furthest from the diagonal. So this is a common problem in the estimation of covariance matrices in signal processing. Such a covariance matrix is called a banded covariance matrix. And maybe a future direction in data analysis would be to apply these techniques from signal processing to correlated chi-square. Anyway, that's just something for you guys. Anyway, this was the exercise I gave you guys last time. That concludes our discussion of correlated chi-square fitting. If anyone has any. Okay. All right. The next topic I want to talk about is motivated by consideration of the errors on the fit parameters that we've been talking about determining. So if you're in the Gaussian regime, by Gaussian regime, I mean that the central limit theorem is a good approximation to your errors. You can estimate the errors on these fit parameters just by straightforward error propagation. In fact, the errors I gave for the simple linear fit a few slides ago are just that. So you see here, I give estimates for the errors on the fit parameters as well as the covariance between them. Those are just obtained by naive error propagation, which is fine if you're in this Gaussian regime. However, what if you're not? If the number of measurements you have is small, then these naive estimates of the errors are typically bad. So one solution to this small statistics problem is resampling. So I'll talk about two different resampling programs today, the Jackknife and the Bootstrap. Generally, resampling takes the original data set that you have and creates additional data sets by taking a subset of the elements from that original data set. Jackknife and Bootstrap each do these in different ways, so we'll talk about those now. First, Jackknife. This is actually old. I didn't put the year, but I think it's sometime in the early 50s that these guys in Princeton came up with this method. So just to set up the problem here, if we have a certain number of m primary observables that we measure directly from our data, and we wish to estimate secondary observables that are functions of the primary observables, we're going to denote those secondary observables by capital Y. And you can think of these secondary observables as arbitrary functions of the means of the primary observables, such as the fit parameters that we considered in the previous example. So before we start discussing ways to estimate the error different from error propagation, let me just stress something that sometimes gets lost. The best estimates of these secondary observables are given simply by taking the means, the sample means of the primaries, and plugging them into this function, right? So I haven't done any resampling or anything like that. If I want the best estimate for my complicated quantity, I do that on the original data set, and that's it. That's the best estimate. All other estimates could be biased. So don't mess up. Don't mess with that. The thing you quote as the answer should not depend on your resampling. Okay. So here's how Jackknife works. We form these Jackknife replicas of the sample means. So now this is a bit of a strange notation here, maybe. Remember we had m different primary observables. Each one of those observables has n different measurements of it. So this first index here, I, is the same as this index, the one that goes from 1 to m. And the second index, k, is the index that goes from 1 to n, which is over the measurements of that particular primary observable. So you can see here that I'm concerned with primary observable I, but if I want to form the jth Jackknife replica of this primary observable, I take the average over all of the original data sets, excluding the jth one, right? So I have a list of all the measurements of a particular observable. I remove one, and then I take the average. That gives me a jackknife replica of the mean of that primary observable. Similarly, so throughout the notes so far, we've been using this hat to denote the sample means. I'm going to introduce this bar here, which is the mean over all of the jackknife replica, right? Now again, this should not be used as your best estimate of the quantity that you're interested in. That is reserved for the sample means without doing any resampling. So this is just used in estimates of the jackknife error, which we'll discuss later. So once I've got these jackknife replica of the means, I can form jackknife replica of the secondary observables that I'm interested in. So that's very straightforward. I just plug them through the machinery that is these f functions right here, and I get jackknife replica of the secondary observables. So there are, in general, n different jackknife replica for the secondary observables and the primary observables that are obtained from removing each of the n possible measurements. Okay, so everyone understand this jackknife procedure so far? You remove things, then you take the average, then you plug them in to get secondary observables. Once you have these replica at your disposal, you can estimate the errors and the covariance by using these formulae here. Now, notice that this is a bit maybe surprising. This is the error, this is the jackknife error estimate, but it has no characteristic 1 over n prefactor. So you might naively think that this error doesn't behave right. It doesn't decrease as we increase the number of measurements. Oh, there should be a squared there, sorry. This is the variance actually. So if I were going to quote an error estimate, I would take the square root of the right-hand side. So I'll correct that. Anyway, similarly, when we estimated the variance using the standard classical estimator, we had a 1 over n, or a 1 over n minus 1. But here, you see that that factor in front tends to 1. But in fact, that's correct, because if you recall, there already is a factor of 1 over n inherent in each of these numbers. So as we increase the size of our data set, the spread between these numbers will all decrease like 1 over n because they themselves are averages. So that's why you don't need an extra factor of 1 over n out here. In fact, I encourage you to justify this to yourself by just considering a primary observable in here instead of a secondary observable. And you'll see immediately that this, with this factor, reduces to the standard estimate of the variance. Similarly, you can generalize this estimate of the variance, well, I should say the error, sorry, to the covariance in this same manner. One of the key advantages to jackknife and these resampling plans in general is that you can iterate this process any number of times very easily. In practice, how this works is you store the, again, this index I goes from 1 to m over the number of different observables that I have. I store all of these sample means. Remember, these depend not on the resampling at all. And I also store all the jackknife replica of these guys. J goes from 1 to n in a vector, like this, right? Then I just write my routines that give me the secondary observables to operate on this vector, right? So then I get y, I, r, and then my jackknife replica of the y's. Equals some function of these guys. If you retain these guys, you can then reconstruct additional secondary observables from them, like I've written here. So what I'm trying to stress is that these jackknife replicas can be passed around so that you can correctly propagate the errors, taking into account all the correlations between these different observables very easily. Remember, if I was doing error propagation of some complicated function, I would need to take all these derivatives, right? I'd have terms that look like, and then I'd have a covariance between xi and xj. This is all inherent in this jackknife program. So you don't have to explicitly take into account the covariance. Passing around these jackknife replica will take into account the covariance for you. This is a very convenient way to also treat the covariance between different primary observables. In particular, because I can now estimate the covariance between secondary observables, I can do fits. For example, correlated fits, correlated chi-squared fits that involve secondary observables rather than just primary observables. So that's very handy. Okay, that's jackknife. Another method of resampling is called bootstrap, which is more flexible, but albeit more computationally intensive than jackknife. This is much newer. It's these guys at, I forget where they were. I think it was Caltech or Stanford, someplace on the West Coast. Efron and Tibshirani. I want to say it's Berkeley. It's Berkeley. Sorry, it's Berkeley. Anyway, not that matters. All right, so the bootstrap replica are created in a different way than the jackknife replica. Here's our bootstrap replica of the primary observable mean. Now, what we do there is instead of removing one of the original data sets, we generate a new data set that has the same number of elements by drawing with replacement from the old data set. So just to illustrate, say my original data set had 5 elements in it: x1, x2, x3, x4, x5. My sample mean, here we go, x bar, that's the average over all of these. Now here's my first bootstrap replica of the sample mean. Okay, I put that bootstrap index as an upper index. So I'm going to draw 5 elements from this original data set with replacement. I might have duplicates. For example, I might have x1, x1, x3, x2, x5. How many is this? 1, 2, 3, 4, 5. There's a bootstrap replica of my data set. I average over these guys and get a new bootstrap replica of the mean. And I keep doing this, right? Again, just a randomly chosen data set that has the same number of elements. That's a bootstrap replica. Obviously, you can see here that while in jackknife we had a limit on the number of jackknife replica, we could only have n jackknife replica from removing all of the n elements of the data set. Here, there's no limit on the number of replica. I can keep doing this as many times as I like, certainly more than 5. I could do it 1,000,000 times. So there are a great many more bootstrap replica than there are jackknife replica. Again, everything proceeds as normal. I take the average over the bootstrap replica. Notice I've had to specify NB as a free parameter, the number of bootstrap replica, because that's something I choose myself. I don't have to force NB to be equal to n. And then I, again, construct the replica of the secondary observables. That should be an NB. Oops. It should be an NB there. This is the same formula, basically. Okay. Furthermore, because of this somewhat more random procedure for generating the replica, our estimate for the covariance looks different than it did for the jackknife. Here we do have this suppression, 1 over NB. That's because if I increase the number of bootstrap replica, I'm not necessarily guaranteed to decrease the differences here, right? So in order to get the correct formula for the bootstrap covariance, I need to put this 1 over NB. Again, if you look at a primary observable for y, you can see with a bit more algebra that this reproduces the correct estimates for the error. with this 1 over NB here. Okay. Questions on Bootstrap so far?
So, for the bootstrap, you're saying that the distribution is random when we are choosing it.
Yes.
But it is not random. We know when we do it in computers, there might be correlations, right?
That's correct.
How are you getting rid of that correlation?
You mean correlations between, say, this data set and the next data set? Well, first, let me say a few things about that. Number one, I'm assuming that my random number is sufficiently good, such that there are no correlations between the elements chosen in this bootstrap replica and the elements chosen in this bootstrap.
Yeah, between two bootstrap samples.
Yeah. I'm assuming those correlations are absent. So if you use a crappy random number generator, then yeah, you'll have correlations between this and this. But I should say that there are no correlations in here, right? It's not
in there, it's not in there, but in bootstrap, like set of another 5.
Yep. Right. Those could be present if you're using something bad, but they shouldn't be present if you're using a good random number.
But there would be some non-zero covariance there.
Between these?
Yeah. We never have a true random generator.
Yeah, all right. But if you're using something like the Mersenne twister, I implore you to demonstrate that there's evidence of covariance between these. I do not think you will see it. One thing I'll say though, it's also very handy when generating these bootstrap samples to remember the seed that you used for your random number generator.
So that it's different next.
Exactly. Okay. So that, in some sense, the random choices for the different bootstrap samples are reproducible, right? Mm-hmm. So if someone else does your analysis and they want to see if they get the exact same bootstrap error as you, they can reproduce exactly what you've chosen.
Yeah, with the same seeds.
Yeah. So also, if you then want to bootstrap the data and do another analysis and then combine bootstrap samples later, like I suggested with the tertiary observables, you're going to need to do the exact same sampling. So it really makes sense to remember the seed that you used so that you can generate the exact same set of bootstrap samples again. Okay. Other bootstrap questions?
So the idea is that we reproduce the error through the jackknife or the bootstrap, but the mean, the estimate should be from the initial data, not use the...
Bingo. That is the best estimate of the mean. That is unbiased, and these estimates of the mean do have a bias that vanishes with 1 over n.
Oh, okay.
Yeah. That's the. I mean, it's small if n's big enough, but again, the whole reason we were doing this was that n wasn't big enough, so you don't want to use that. In fact, you can use that as a test to see generally exactly how big these biases will be. Okay. All right. In addition to this error formula, which is sort of the analog of the jackknife error formula, when you use Bootstrap, you get access to a whole host of other information. Because you are unlimited in the number of Bootstrap samples you choose here, provided your data set is big enough, provided n is big enough, you can actually get some information on the distribution of secondary observables. Now, the example I'm using here is from that last exercise I gave you about correlated chi-squared fitting. I've resampled my data into 800 Bootstrap samples, and I've performed a correlated chi-squared fit to obtain a correlated chi-squared fit to the data on each one of those 800 Bootstrap samples. So I have 800 values for the minimum correlated chi-square, right? I can now verify that this thing is actually chi-squared distributed, right? I mean, there was no way I could have done this had I not done any resampling, right? If I hadn't done any resampling, I would have gotten one correlated chi-squared and an error. Maybe my minimizer would have given me some information about how uncertain the minimum it found was. But here I can actually verify that this thing is indeed distributed according to the chi-squared distribution by just histogramming all these different chi-squareds that I got. And you can see that this does look quite chi-squared distributed. There's this long tail, and it's peaked around the value that you get on the mean. Using this, using these bootstrap samples, you can actually estimate the distributions of secondary observables to actually check and see if you're indeed in the Gaussian regime or not. If the distributions look Gaussian, then yeah, you probably feel more comfortable. But here's one that, well, it shouldn't be Gaussian, but you can verify that it's distributed according to your intuition. We can take this a bit further and use these bootstrap samples to estimate confidence intervals in a different way. So what we've been doing to estimate confidence intervals so far is to estimate the variance and then use that as our symmetric 1 sigma confidence interval. However, with these bootstrap samples, you can do a brute force calculation of what the 1 sigma confidence interval is. Remember, the interpretation that we had of the 1 sigma confidence interval was that the probability that our estimator for something, I'll call that y hat, was between an interval of the true answer, which I'll call mu y. So maybe I say mu y, trying to write it in an asymmetric way. Let's say mu y minus a, y hat, mu y plus b. And then we said that this probability was equal to 0.68. This defined what the 1 sigma confidence interval was. Before, we had just an a symmetric expression for this confidence interval. But, sorry?
Could I ask a question?
Sure, yeah.
How do these formula change if my primary observables are not independent?
If my primary observables are not independent, they don't change at all. That's one of the beauties of all these methods. I haven't assumed that my primary observables are independent. Nowhere did I need that. I can create these replica, fine. Yeah, it works fine. Yeah, that's a really nice thing about it. Like I said, you don't need any of these terms explicitly included in your error estimate.
That's why we are calculating the covariance matrix, right? When we estimate the parameters.
Well, that's two different things. I've done correlated chi-squared fitting, where I require the covariance matrix,
Yes.
because I wish to take that explicitly into account when I estimate my best fit values.
Yeah.
But say I had a simple function of, say I had a secondary observable, which was, I don't know, a function of two primary observables, just x1 squared plus x2 squared, right? Like this. If I wanted to propagate the error naively, I would write sigma y squared is equal to, I don't know, if this is f of x1,
Yeah.
x2, I'd have derivative terms like this. I'd have partial f partial x1 squared sigma x1 squared plus partial f partial x2 squared sigma x2 squared, and then I'd have this plus 2 times partial f partial x1 partial f partial x2 cove
Yeah.
x1 x2. If I use the jackknife estimate for sigma y, I don't need to do any of this. The correlation between x1 and x2 is taken into account automatically. So none of that is required. But so these two issues are different. We estimate the covariance because we need to define the correlated chi-square, but the bootstrap and the jackknife procedure take into account the correlations between the primaries. Okay. Right.
Now,
Sorry,
Go ahead. Yeah, no.
now I'm confused because I thought that this is why the discussion we were having last week that we should plug in correlated primaries.
No. Now, there's correlation and there's autocorrelation.
Okay.
Yeah.
That's what I mean. Okay.
Correlation's fine, autocorrelation is not fine.
All right.
We also mentioned this just at the beginning of class here. I've assumed no autocorrelation.
Okay.
That's in the index that goes from 1 to n,
Yes.
but I have allowed correlation in the index that goes from 1 to m
Okay.
over all my primaries.
Okay. Good.
Yeah. Okay. All right. So anyway, back to these kind of strange estimators for the 1 sigma confidence interval. I can really take this definition in a straightforward manner of what a confidence interval is and just use the values that I get on all of my different bootstrap replica to estimate this confidence interval. For example, if I wanted the lower end of this confidence interval, I would sort all of my replica of the secondary observable. So remember, these indices were arbitrary anyway, so now I'm just sorting them so that the smallest one is the one with the superscript 1, and the largest one is the one with the superscript MB. And then I just take the 16th percentile value, and that is, in fact, guaranteed to reproduce this definition of the confidence interval. Similarly, on the upper end, I can just take the 84th percentile value, and that's my confidence interval.
How do you find that 16th percentile corresponds to?
Well, say I had 1,000 bootstrap samples.
Yes.
Then I would just take the 16th one after I sorted them. And then I would take that value, and that would be my lower end. For example, all I'm doing, right, if I histogrammed all those bootstrap samples, right, I'd get a histogram that looked Gaussian, maybe, if I was in the Gaussian regime, right? And then when I take the 16th percentile, I'm taking this guy. And then when I take the 84th percentile, I'm taking this guy. So that this shaded region here corresponds to 32%,
Yeah.
which means the 68 confidence level. So that's how I got those two estimators up there. If I instead
You're
this
just taking like 16 plus 68 plus 84.
yeah, exactly that's all yeah exactly. So if I write them out in a list and I pick the 16th percentile and the 84th percentile, I'm guaranteed that 68% of my bootstrap samples lie between that range. So yeah, you can use this to estimate any confidence interval you want. And you can see that if you have an asymmetric distribution like that chi-square distribution that I showed before, these confidence intervals won't necessarily be symmetric. You can reflect asymmetric confidence intervals using this definition. This is obviously important outside the Gaussian regime where you don't know you have a Gaussian to start with. And it's especially important if you have heavy-tailed distributions like that chi-square one, actually.
So that means that the error bars will not be symmetric
Exactly.
around the mean.
Yeah, exactly.
Okay, but okay, that makes sense.
I mean, it depends on how the
You don't
mean.
have to know the distribution. I mean, it's not directly blind.
Exactly. These methods all go under the category of non-parametric statistics. Right? You don't know what the underlying distribution is, but you can still estimate things about that. Yeah, exactly. For example, if the quantity of interest you had was chi-square distributed, why would you quote a symmetric error interval, right? I mean, you know that 68% lie in this asymmetric interval. So that's what you should quote. Okay. Last thing I've done here is provided a visualization of the correlation. This is again that example I gave you guys of correlated chi-square fitting. Remember, it was a 2-parameter fit to this exponential ansatz that we did. I did it 800 times on 800 different bootstrap samples, and then just put an XY scatter plot here of the results. And you can see here that there is some significant correlation between these 2 parameters, as you'd expect. You know, if the minimizer finds one a little high, it might find the other one a little low. So you can actually see this ellipse tilt here a little bit, so that if you were drawing, you know, your joint confidence intervals, you'd probably have these tilted ellipses here for maybe the 1 or 2 sigma confidence intervals. And again, this brute force way of estimating probabilities you can use to estimate p-values, provided you have lots of bootstrap samples for the test statistic. Okay, that's all I want to say about Bootstrap. It's super powerful. I'm a big fan of Bootstrap. Okay, the last topic, which I'll get to in the last 20 minutes here, is what to do if you are doing Markov chain Monte Carlo. Now, so far, we've considered all of the elements in our data set, all of the measurements, to be independent. But if you're doing a Markov chain Monte Carlo calculation, they're not independent. Just to motivate the fact that I am born to talk about Markov chains, Andrei Markov, the inventor of Markov chains, and I share the same birthday. This was his Facebook avatar, actually. Andrei Markov was motivated because he wanted to generalize the central limit theorem for variables that weren't independent, right? So the first application of a Markov chain, anyone know? What his first test case of a Markov chain was? Well, he was a big fan of Russian poetry, Pushkin. He found that the occurrence of a consonant or a vowel was not independent and identically distributed, right? It depended on the preceding letter. So that's a probability of getting a vowel or a consonant in Pushkin's poetry is the first Markov chain. Okay. Well, I guess the whole top of this is going to be cut off here. Huh? Maybe I'll do that. All right, so I'll breeze through this really quickly. Just crash course on how Markov chain Monte Carlo works. I've used notation that's similar to what you'd expect in quantum mechanics. There's the state that belongs in the state space, and then here's the state of the system at a particular time in the Markov chain, which could be a superposition of elements in the state space. If I want, given a current state of the system, if I want the probability that the system is in a particular state, then I have to form this inner product, and that gives me the probability that the system is in a particular state. The Markov chain comes in where I specify how to go from the state of the system at time t to the state of the system at time t plus 1, and that involves this Markov matrix. Yeah. Okay. Maybe I have to actually scroll. Whoa. Okay, first we have to start off the Markov chain somehow. There are 2 sort of broad ways of doing this. There's a hot start and a cold start. Hot start is where I uniformly choose the starting configuration from the state space, and a cold start is where I choose a particular configuration to start. These are these probabilities that are matrix elements. These are these transition probabilities, which are matrix elements of the Markov matrix. They have to be normalized so that if you start in some state, you'll go somewhere. Very important property of Markov chains is ergodicity. So ergodicity, a Markov chain is ergodic if it satisfies these 3 sub-properties. If it's irreducible, which means that you can transition between all states that are possible. If it's aperiodic, which means that you don't have any cycles of hopping from one state to another state and then back again. And it has to be positive recurrent, which means that if I'm in a particular state, there has to be a finite probability that I return to that state after a finite number of steps. So I won't wander off into oblivion. So that's what it means for a Markov chain to be ergodic. A Markov chain satisfies detailed balance if it satisfies this equation for some particular distribution pi. And the reason I bring up detailed balance is that there's this theorem which governs how Markov chains behave. So if a Markov chain is ergodic and satisfies detailed balance with the distribution pi, then this distribution is stationary, which means that the Markov chain isn't going to move away from it. It's unique, which means there's no other stationary distributions. And it's universal, which means that irrespective of my starting criterion, I will tend towards this limiting distribution. So this is the fundamental theorem of Markov chains and governs when they have a suitable limit, a stationary limit. Okay. Obviously, this stationary state here can be viewed as an eigenvector or right eigenvector of the Markov matrix with eigenvalue 1. Just that's the defining equation. Generally, left and right eigenvalues are different. For example, I can quite easily construct a left eigenvector of the Markov matrix by just looking at this normalization criteria, which says that if I start somewhere, I have to go somewhere. So obviously, the constant vector in state space is a left eigenvector of a Markov matrix with eigenvalue 1. But that's a trivial statement. Doesn't mean it's a right eigenvector. Okay. All right. So what do we actually want to measure when we do these calculations? Typically, we want to measure the expectation value of things, functions, in between the stationary states. So if I just put in a complete set of states like you would in quantum mechanics, I get the normal formula for expectation value. But here's the non-trivial part that makes Markov chains particularly tricky to analyze. We can define this thing, an autocorrelation function. Now, these f sub tau and f sub t plus tau are this observable f measured on different elements of the Markov chain. So you'll see here that it doesn't necessarily matter what tau is, it just matters the separation between this guy and this guy. So this quantity here, the expectation value of these product of fluctuations is called the autocovariance. Even though I called it the autocorrelation, it's, I think, formally called the autocovariance. Obviously, if t equals 0, this thing is just equal to the ordinary variance. So it's quite common to define the normalized autocorrelation function by dividing this thing by the value at t equals 0. So that at t equals 0, this thing is normalized to 1. So this thing is a measure of how correlated successive elements in the Markov chain are. Now, can we get a handle on how this thing behaves directly from the Markov matrix? Because the Markov chain is specified by the Markov matrix. And the answer is yes. So if I wanted to analyze this expectation value in terms of the Markov matrix, it's formally just this product here, where I have the observable of interest, and then I have to put the Markov matrix inside it to a suitable power, just like you would in quantum mechanics. And now I'll do a spectral decomposition of the Markov matrix to get the eigenvalues of the Markov matrix right here. Now, you can prove that stochastic matrices like the Markov matrix have particular properties for their eigenvalues. Namely, that the eigenvalue of smallest modulus is always the unit eigenvalue. All other eigenvalues have to have larger modulus than that first one. So because of that, smaller modulus. The largest modulus eigenvalue is the unit eigenvalue. All other eigenvalues have to have smaller modulus. If I set this, if I look at the n equals 0 term in this sum, I know that that lambda is equal to unity, and that's what gives me this first term here, which is what I would have gotten had these two things not had any correlation between them. But now if I consider the remaining terms in this sum, I know that these guys are all less than 1, but they don't necessarily have to be real. There could be some sort of oscillatory component to them. But I'll just estimate their size generically as this exponential factor here, where I've defined the decay constant in this canonical way. So this time here, tau x, governs the asymptotic approach of the autocorrelation function to the decorrelated case. So this is the relevant time scale for how long it takes for the Markov chain to completely decorrelate, and it's linked to the second largest eigenvalue modulus of the Markov matrix. Okay. Now, in addition to tau x, which I defined on the previous slide, there's also tau int, which is defined in this way from the autocorrelation function. Now I should say here that formally we've defined this autocorrelation function for a particular observable, right? So the autocorrelation function depends on which observable you're talking about. However, you can see that this tau x is independent of the observable that we considered. This is a property of the Markov matrix only. So you could probably come up with observables that for some crazy reason have no overlap onto the second largest eigenvector, and therefore would not be governed by this tau x. But in general, tau x is governed by the second largest eigenvalue modulus. That's a property of the Markov chain. Tau int, however, does depend on the observable, much more strongly. So you might guess that this doesn't depend only on the asymptotic behavior of rho, but also on the integral of rho. So rho over all times. So you could guess that this is more dependent on the observable. So the formal definition of the integrated autocorrelation time is this. There's this 1/2 for convention, and then you sum from 0 to infinity the autocorrelation function. In practice, as you increase t, you'll have fewer and fewer measurements on a realistic data set. I mean, if I wanted to estimate the autocorrelation function on a data set with so many elements in it, well, estimating the autocorrelation function at time t equal 1 is quite easy. I just take this guy and this guy, make that product. Then I can also take this guy and this guy, this guy and this guy. So I get a lot of measurements of the autocorrelation function at separation 1. But as I increase the separation, say separation 5 or 6, and I want to take this guy and this guy, well, I don't have as many measurements of that, right? I can only do this, then I run out because. As time increases, rho of t becomes less and less well determined. In fact, rho of t also decays quite rapidly, so it's a very reasonable thing to do to truncate this estimate of the integrated autocorrelation time by introducing this upper bound to the sum. This is, there's a very sensible way to choose this W by making a compromise between the truncation error that you get, and therefore a systematic error in the estimate of tau int, and the statistical error that you have on rho because of this finite data set size. So those two factors are taken into account in the criteria discussed in this paper for how to estimate W. But you can see that it doesn't matter so much. Well, here, okay, this is just what I said. There are statistical errors associated with rho and thus with tau int. They're given here. So this competition between statistical and systematic errors is what drives you to. Okay. Anyway, so why should I care about autocorrelations? Well, the answer is that they affect this thing that Andrei Markov set out to do, which was the M-dependent central limit theorem, to generalize the central limit theorem for Markov chains. Here's our M-dependent central limit theorem. In addition to the criteria that the variance of this particular random variable is finite, you also have to have that the sum over the autocorrelation function is finite. And then you get the familiar distribution of the sample mean. However, the parameter that governs the width of the distribution of the sample mean depends on tau int. Remember, tau int is different for every observable, so this tau int is the one calculated for this particular observable. That's why we had this factor of 2 here. If tau int receives no contributions from the autocorrelation, then it's equal to 1/2 and you recover the original formula. You can now use this to estimate statistical errors when you are dealing with a Markov chain. Another technique is to simply obliterate the autocorrelations by so-called binning. So say you have a data set, x1, x2, x3, xn, and you have measured the autocorrelation on this data set, and you have observed that tau x is around 2. So if you get a new data set from this original data set by averaging successive elements, like this. So now I have my new x tilde 1 all the way down to x tilde n over 2. This new data set has a reduced autocorrelation time. It's now equal to 1. So on and so forth. The general rule of thumb is if you average successive measurements such that the size of each bin that you make here is equal to something like 2 times tau x, then the resultant bin measurements exhibit no autocorrelation.
Looks a bit similar. I mean, if you had it in the simulation already, in terms of coarse graining in the simulation, would that actually, so because sometimes the multi-grid that comes actually to play, but that's then of course physical, so it's not the data set, but it's the actual lattice then.
Exactly. I mean, another way to view this is when all you guys did your first Ising model calculation, right? You just skip. You do 20 or 100 Markov steps, and then you measure, and then you do another 20 or 100. An alternative to that would be to just bin the data if you measured every single time. But yeah, you're right. It's sort of in the same spirit as multi-grid. You want the long distance fluctuations of the data. You don't want to be bothered by these short distance fluctuations. So it's like a multi-grid in one dimension. In addition to taking into account the integrated autocorrelation time explicitly, you can bin by doing this, and then you can forget about the autocorrelation. However, tau x can be very large, so maybe sometimes you can't bin the data set to get rid of it.
Tau s depends upon m, right?
Yes.
The eigenvalues of only m.
Yes, that's right, not the observable. Yeah. So formally, if you bin in tau int, you're not guaranteed to reproduce the ordinary central limit theorem. Your bin sizes have to be comparable to tau x, not tau int. So that's.
What's the significance of tau s? I mean, why do we need tau s in first place?
When you prove this M-dependent central limit theorem, you have to neglect autocorrelations between elements in the Markov chain separated by at least capital M steps. So even if you're separated by more than tau int steps, that doesn't necessarily mean that autocorrelation is absent, right? Autocorrelation is only absent after tau x steps, because that's when the asymptotic behavior of the autocorrelation function
Yes.
falls. So this is a sore point, but that's the truth. In order to prove this M-dependent central limit theorem, you need bins that are of size tau x, not tau int.
And in practice, the tau x would be taken from fitting the autocorrelation.
Yes,
or
that's-
by taking the logarithm and then
Looking at the effective, yeah,
slope.
yeah, exactly. Yeah, that's right. I'll do an example which hopefully illustrates all these things in the last few minutes here. Wow. Okay, this will take a few minutes. Sorry. So the example, just to demonstrate that all these considerations that have seemed kind of airy-fairy from the M-dependent central limit theorem are indeed real, I've constructed a very simple random walk here. This is just a 1D symmetric random walk on the interval -5 to 5. So it's the Markov chain is you just hop either left or right with equal probability. If you're at one of the endpoints, then you either hop away from the endpoint or you stay where you are with equal probability. This last step is needed to ensure aperiodicity and therefore ergodicity of the Markov chain. It's also quite easy to figure out what the stationary distribution of this chain is. It's the uniform distribution on these 5 sites. So after thermalization, we're going to head for the uniform distribution. So we can take a look at that. So here's thermalization. I've run 1,000 independent Markov chains and then histogrammed their positions, all starting at 0 after 2 steps of the Markov chain. And you can see that predictably, you can either end up at 0 or 2, right? Because you could hop twice and hop, or sorry, 0 or 1. So you could hop once and then hop back, or hop once and hop back. Here's after 6, you can see you can actually reach the sides, and then you can hop back towards the center. But you can see you still have quite a strong memory of the starting point here. That gets obliterated as you increase the number of steps of the Markov chain, finally by something like 10,000 steps. You've lost all memory, and all these chains are equilibrium distributed. So let's assume we're thermalized. None of this central limit theorem stuff applies if we're not thermalized. All right, now we're thermalized. We can calculate the autocorrelation. I've only measured every 10 steps of the Markov chain. Then I've estimated the autocorrelation function. You can see I get this nice exponential fall off. If I were to take the logarithm of this, I could resolve tau x. If I were to integrate this numerically, I would get tau int. That's what I've done here. Here's tau int as a function of the upper bound of the sum. And you can see it converges pretty well. So in practice, it doesn't really matter which value of w I take in here. I'll all get a very similar value of tau int. It's probably around 2.5. But remember, I only measured every 10, so it's really 25. Okay. All right. Now I can histogram the sample mean. And you can see that here's 500 measurements of the equilibrium chain. Here's 1,000. You can see it gets narrower, and it gets narrower still after 2,000. So that's what you expect. I can also calculate the width of this sample mean, and it's exactly what I would have expected from the M-dependent central limit theorem. So if I just take the square root of 2 times tau int times sigma, sigma squared is about 10. I just measured that. That's the ordinary variance. So if I calculate this, I see it should be about 22. And then if I calculate the root mean squared of this thing and then multiply by the number of measurements square root to get the variance, I get also 22. So the M-dependent central limit theorem works perfectly, even for this silly example with a small number of measurements. just to drive home the point that we'd be underestimating the variance by about an order of magnitude if we didn't take into account the autocorrelation. Tau int was about 10. It was about 25. So 2 times 25, take the square root of that, and that'd be the factor that you got wrong. Anyway, autocorrelations are important when you're taking into account. You can either treat them explicitly or bin to get rid of them, but you have to do something, and that's it. Okay. Final questions about any of it. All this is online.
I didn't get, you said that integrated autocorrelation time notated by just summing over the distribution, which is also scaled to first to 1, right? As you did. It began from 1.
Rho. So rho of 0 is 1. Yeah, but my definition of tau int was a bit different. This was 1/2 plus the sum from t equals 1 to w of rho. So I didn't include this term in the sum. This term is considered explicitly by this thing here, right? The formal definition of tau int can also be the sum from minus infinity to infinity of rho, but then there's a factor of 1/2 in the front. So it's a question of where you put this factor of 2.
Okay. So you get the symmetrical.
Yeah. I mean, this thing is symmetric, so I just, Right, the t equals 0 term, well, if I write it this way, then I have to put a 1/2 here. But if I don't put this 1/2 here, then there's no factor of 2 in the modified variance.
Yes.
So put a 2 here and a 1/2 here, or what? Okay. Just a word about tomorrow. Tomorrow is your soft skills day. The soft skills workshop in lieu of the construction is going to be held in the Matt's seminar room, which is like in this labyrinthine building in Westland Row. It's very hard to get to. So if you know where the new Matt's seminar room is already, great. Just go there. If you don't, you can do 2 things. You can ask in the Matt's office, or if you show up at, I think the thing starts at 9:30. If you show up at 9:15, 9:20 in front of the Sing lecture theater, I'll be there, and then I'll wait till 9:28 or something, and then I'll walk up to the Matt's seminar room with you guys if you want.
I think that would be great, but probably most of us don't know where this is.
Okay, yeah, all right. So yeah, I'll wait for you guys tomorrow.
Okay.
In front of the Sing, yeah. We'll all have our ears covered because there'll be all this jackhammering in the Hamilton Cafe. Okay.